Math movies. Yeah, you heard me. Count you in. Coming up next on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Faith Saley, and today we're joined by author and cosmologist Janna Levin to talk about great math movies. Welcome, Jana.
Thanks for having me.
Thank you for joining us. I have to ask, you're an attractive woman. Have you ever told someone you're a cosmologist and they assume that you do makeup?
Yes, first, right, exactly. First I explain the stars to them and then I do their makeup, right? That's usually how it works.
Yeah, I work on stars. Yeah, exactly.
Their makeup doesn't look too good when I'm done, but yeah, that's how it works.
In the 2015 biopic The Man Who Knew Infinity, Dev Patel plays Srinivasa Ramanujan. And in the film, real-life Cambridge mathematician G.H. Hardy tells Ramanujan that his formulas are not enough. He has to create the proofs. So, Jana, let's clarify things a bit for our audience. What is the difference between a formula and a proof?
Well, here's a formula. E equals mc squared. Einstein's most famous formula, the most famous equation ever written. It says one thing equals another thing. But that's not the proof. That didn't drop out of the air. It didn't hit him like, you know, a rock falling from the sky. He had to derive that E equals mc squared, that equation, that energy can be, is basically locked in the mass of a particle. He derived it by thinking about space-time. And it seems like a far reach from space-time to energy, but a proof is when you start with very simple principles, his very simple principle being this unification of space and time, that time is like another dimension. And from it, work your way step by step until you come to the formula at the end. And if the proof is flawless, we all have to agree on it. It's one of the most beautiful things about mathematics is that it transcends argument. We don't sit here discussing what did Einstein mean. You know, you go to a philosophy class, we're still arguing about what Kant meant or something like that. You know, it drives me crazy, but we know exactly what Einstein meant because he showed us a proof. And so we don't have to sit here and be racking our brains. What did Einstein mean? It's a gift. It belongs to all of us once it's given to us.
Do you think that's a characteristic of people who choose to be mathematicians, is that they really like that clarity, that they would just go bonkers in a philosophy class?
Well, honestly, it's absolutely, but also to some extent, mathematicians go bonkers with physicists. So physicists we're like plumbers, you know, we just grab tools and start using them, you know, and mathematicians will not accept 1 + 1 is 2. I will, as a physicist, and move on from there. But a mathematician has to have a proof of it. And a proof of 1 + 1 = 2 comes in deep in like the Principia Mathematica or whatever. You know, it's not something that's easy to prove, actually.
And we see this in the film, The Man Who Knew Infinity, because Ramanujan is sort of hit by formulas, like you say Einstein was not, right? He talks about how he gets his math from the gods. It's all very intuitive.
Well, Einstein was incredibly intuitive too. He understood, for instance, his theory of curved space-time before he had the mathematics for it, meaning he had the intuition, but he didn't have the mathematical description in place for a long time, over a decade it took him. And he needed help from mathematicians. So he had this intuition that things fall around the Earth because they're following curves in space-time that the Earth has created. But he didn't have the mathematical description of exactly how the Earth changed the shape of space-time or exactly how things fell along the curves. And that was very hard.
Is that how the biggest breakthroughs in mathematics have taken place with certain, well, mostly from what we know from history, certain men who have had these massive bouts of intuition and then have to spend years supporting them?
I should say there's a lot of really accomplished female mathematicians. For whatever reason, mathematics was a field where there was a lot of accomplished women, but
that's good to know.
Yeah,
but we don't have biopics
about them.
Right,
where's the biopic about Emily Noether? But the question was, does it just sort of come out of the sky for them, or is there an intuition? I mean, there is, I think, a sense that some people just see things. Have you ever seen someone solve a Rubik's Cube or one of those geometric locks, and you can just sort of spatially see it sometimes. And the action,
Do you
sometimes, I mean, sometimes I see solutions that are novel. Yeah. I mean,
how does that feel?
It's amazing. It's a wonderful feeling. It's why we do it, because most of the time it's sheer frustration. I mean, all of us are working at the edge of our capacity, meaning we're not trying to solve the easiest problems we can. We're trying to solve the hardest problems we can. So we're as practicing scientists, pushing ourselves to the point of frustration, where we're not sure there's a solution, or if we'll find it, if it exists. So those days when you do find it, you know, it's extremely rewarding, and it's this wonderful communion sort of with something bigger than yourself, you know.
And in your life, on average, how often does one of those days come up? One out of every...
Don't make me list the percentage. I'll be really depressed. You know?
This is why I think
it's not that often. I mean, it's not, you know, I like to publish just a couple of papers a year, a few papers a year, and those will be based on, you know, hopefully these nice solutions that we find. So it's not that often.
This is why I think scientists are so heroic, because everyone who's come on the show talks about this embrace of not knowing, an embrace of failure, failing your way to answers, and then being comfortable thinking, I may never know that answer in my lifetime, but I'm part of something bigger.
Yeah, I mean, my first book was really about something I knew we would never know the answer to, whether or not the universe was infinite. And the book wasn't just about whether or not the universe was infinite, it was about the not ever knowing. And how that's a strange position to be in when you work on things that won't be resolved in your lifetime. Recently, you know, a very famous scientist was working on a project for the far future, 10, 20 years down the line. He's in his mid-80s, and he said, it won't be in my lifetime, but that doesn't matter. It's a different relationship to the larger scheme of things.
I think it's intellectually generous.
Yeah, I mean, hopefully science is about that generosity. It's you know, we publish for free. All of our content is freely available, and this is all the science that's funded by the government has to be freely released. That's why you have Hubble pictures whenever you want them, and you can use them whenever you want as your screensaver. You don't have to pay for them because you already paid for them by supporting the NASA and the science efforts.
We kind of have to talk about Interstellar.
Okay, yeah.
In that movie, the real non-fictional CGI artists fed data into their art machines and predicted a new and more exact vision of what a black hole looks like. What does it matter what a black hole looks like? Why does that matter?
Well, we've never actually seen one. We see black holes doing things to their environment. We see black holes tearing apart neighboring stars like cotton candy, and we see the effect of that star on the debris of that star, but we can't actually see a black hole. There is an ambition to resolve the actual shadow of a black hole. So a black hole is a region where if even light veers too close, it cannot escape the gravitational pull, and so it creates a dark spot on the sky. If there were a black hole between us and the Milky Way galaxy, we would see its shadow. It's just that it's impossibly small to resolve. But there is a black hole at the center of our galaxy, which is 4 million times the mass of the sun. I think it's a handful of sun widths across, but millions of times the mass. And it's 26,000 light years away. And so trying to take a picture of it, casting essentially a shadow on a very bright region of the galaxy, is like resolving a quarter on the moon, basically. And so there is this ambition called Event Horizon Telescope to do that. If we ever take that picture, it's unclear what the details will, how detailed it will be. But what Interstellar did in their illustration of the black hole, which was nice, is they had this accretion disk around the black hole, this very bright region where matter was falling in. And the accretion disk is just like a ring of Saturn. But the way it looks is it looks like it's above and below the black hole as well, and that's because the light bends from the bright disk and shines like a lens around the black hole. So it would look like they showed it, which was nice that they used that precise sort of illustration.
Yeah, was that one of your moments as a scientist sitting in a movie theater where you're like,
Well, it's
I'm all
funny.
in.
I watched it and I thought, oh yeah, of course it's going to kind of look like that. I hadn't really thought about what it would look like with your, because we don't really hope to see them with telescopes. But I saw it and I was like, oh yeah, of course you're going to see the accretion disk above and below it.
But what you think about, Jana, all the time is what black holes sound like.
Oh,
You
yeah.
were you wrote a book about this. Why are you so keen on what a black hole sounds like?
Actually, the person who wrote the treatment for Interstellar is Kip Thorne. Kip Thorne is a famous astrophysicist, professor emeritus at Caltech, who started with Ray Weiss and Ron Drever, two other people, a project called LIGO. And they started this project 50 years ago. It was an arduous, difficult campaign, and what they wanted to do was record the shape of space-time ringing. And after 50 years, a long development, what they actually recorded the sound of space-time ringing. So here's what happened. It was like 1.3 billion years ago, two black holes orbited and merged and made a bigger black hole. And like mallets on a drum, they rang the shape of space and time itself, like creating ripples. These ripples emanated outward and were on...
The ripples make sound?
Well, okay, if you were floating nearby, it's like a squeezing and stretching of space-time. It could, in principle, conceivably ring your ear mechanism, and you would actually hear it. But what happens is by the time it traveled across the universe and got to LIGO, LIGO was like this instrument ready to record the ringing shape of space-time. It's a huge instrument. There's two machines, 4 kilometers square each. They're very big. And it's kind of like the body of an electric guitar recording the string of an electric guitar. So LIGO is like the body of the instrument, and space-time was like the ringing drum. And it recorded what's known as a chirp, which was a fifth of a second long, the final fraction of a second before the black holes collided.
And
it's pretty crazy. And they played it back to us as sound. They listened to the instrument in the control room. I mean, it's really...
did they know they would eventually hear that? Did they, or something? Or,
well,
or did they just think,
well,
maybe someday?
This was really, I mean, to me, a remarkable story of just sort of strange curiosity, ambition. They did not know black holes were real or that gravitational waves were real at the time that they started. Black holes had never been detected before, and certainly gravitational waves had never been detected before September, a year ago. They started this out of a kind of fantasy. By 50 years on, we have a lot of evidence for black holes, and people certainly believed gravitational waves, these waves in the shape of space-time, would be out there, but they'd never been detected before, and there was a lot of opposition to the project, and a lot of people thought it was futile and it would never succeed. So even going up to the first science runs, they were scared. You know, what if nature doesn't provide enough sources, and they're just listening and it's quiet out there. And so it really took a lot for them to persevere.
When was this chirp heard?
September 14th last year.
And where
just
were
over
you?
A year ago.
I
was printing a copy of the book that I had just written, Black Hole Blues, on this topic while following these guys leading up to the experiment, to give to Kip Thorne, who did the treatment for Interstellar, and Ray Weiss, and I didn't know because I'm not actually in the team, so they didn't tell me for a couple of months. But eventually they basically said, we can't stand it, we have to tell you what just happened. And so I had an epilogue in the book. And they asked me, are you going to rewrite the book now that you know we succeeded? And I thought, there's no way, because it's all about the tension of not knowing. It's all about the crazy ambition. It's about this quixotic campaign. And
or I don't know, would a scientist use the word faith? About the faith that they would hear something one day?
I think, well, you know, Kip was really confident that we were going to detect black holes first. And nobody else was confident about that. But, you know, Kip's amazing. I mean, he was unfazed. And they weren't, if you talk to them afterwards, they're sort of like, yes, we're very satisfied. You know?
They're exhausted. It's taken 50 years.
Right. But, I mean, it really was a triumph. Yeah, it was amazing.
And your group has done an audio modeling of a black hole?
Oh, yeah. So my scientific research was based on a lot of the modeling of black hole collisions. So, you know, unlike the Earth going around the sun in this nice, neat circle, when black holes collide, their orbits are very geometrical. And we use things like number theory, like we were talking about with rational numbers, to make models of these interesting orbits, and we can play back as sound what the gravitational waves would sound like that are emitted.
Well, what does that mean? Do you put math into a machine and get out sound?
Yeah, okay, yeah. So most of our math is pen and paper calculating. Most of the mathematics that I do still. And then at the end, we have a result.
Okay, I just want to stop there because only a true mathematician would say pen and paper. Pencil and eraser for everybody else.
Okay, right, yeah, exactly. Or chalk sometimes in a board, whatever is available. And yeah, we just don't care if we scratch over and it's messy, that's all. But at the end of the day, we'll have some expression. That's a formula versus a proof. At the end of the day, we'll have some expression for how space-time is ringing in response to the motions of the black holes. And that we plug into a computer. And yes, we get the computer to play it back for us as sound. We tell the computer to interpret this as a sound because it's a wave and read the wave. So if I could write a formula for the shape of a ringing drum, I could plug that into a computer and have it emulate the sound of the ringing drum. And
so do you have a lab where every once in a while you hear black holes chirp? What do you think it sounds like?
My lab is really a couch. I'm very, we're not sort of white lab coat, theoretically. But yeah, we students and other professors, we get together and talk about how to find these solutions and how we're going to work on things and how accurately we can know them.
And why does it matter?
There's, by the way, hundreds of people who work on predictions of things like black hole collisions in the world. And so we're hardly the only ones. And other people use much more sophisticated computer modeling, for instance, than we do. The kind of theoretical stuff that we do has a regime of validity. And then there's areas where there are no solutions. We can't calculate at all. And those people do solely on the computers. There's this whole broad spectrum of people who work on these predictions.
And what would you say to someone who says, why does it matter what a black hole sounds like?
I would say, why does it matter that we're not at the center of the solar system? It matters more than we can possibly measure. It has changed our worldview, our notion of who we are, of what this is all about completely. And as we continue and acquire our knowledge and understanding of the universe, that just deepens. It's part of who we are as human beings, I think, to ask who we are in the universe and what's our place here.
So because we have this kind of technology now where we can, we can represent these kind of graphics, do you think that's almost like a new era in mathematics where you can enroll the general public? I mean, I guess by that I mean, is there a, oh my gosh, that's so cool factor that's really sparking people's sort of interest in math? Yeah,
I think we're getting better at conveying our results in ways that are immediately accessible. So I see, for instance, you have this image up about a black hole in front of the galaxy. That's a very sophisticated computer model of a very accurate representation of what that event looked like if you were really nearby, which you would not want to be. But that's real math in that calculation to make that look so precise. It is not a cartoon. That is not an animation. That is a formal mathematical model of two black holes colliding. And as soon as people see it, it's incredible.
It's beautiful.
The intuition, and it's beautiful. Now we can't see it with, exactly. It's awe-inspiring, and we can't get that with telescopes. But what we did get was that little chirp.
Okay, I'm not going to be too proud to admit this. It really, until you said it here, it never occurred to me that we haven't really seen a black hole. I feel like we all think we know so much about black holes now, and we've seen representations like this. That to me, I would thought, oh, that was a satellite that took that.
Exactly. No, we have never taken a picture of a black hole like that. No way.
That's all math.
Nowhere near. That's
when your kid says, "Why do I have to do math?" You can say,
because look at this. Yeah. Definitely. I love that people are now taking the time to make their mathematical results so visually accessible. And it's really neat and powerful. So, even you mentioned some of the animations we do. Those are formal descriptions of black holes orbiting and the path that they take. And just like mallets on a drum, makes different sounds depending on how they move. And so playing it back audio, what it would sound like while watching, the black holes moving. I mean, it just sort of, it's immediately understandable, even if you didn't follow the derivation.
And what does it sound like?
Well, it's sort of disappointing how they sound. So in this kind of circular orbit, as they get closer together, they get faster, which means higher frequency. So it sort of sweeps up in frequency near the collision. So there's this kind of like whoop. And what you're hearing is the black holes moving near the speed of light and faster, and as they get faster and faster, again, just like a drum roll, it sweeps up in frequency.
Which is just not what you would expect if
no, I don't
you're
know.
Making the soundtrack for the movie. It would be like low and huge.
I don't, yeah, exactly. And in fact, they ring space-time in the human auditory range, which is really remarkable. LIGO is sensitive to the same frequency range as the piano. It's just what black holes that size do. For a very large black, I know, how convenient. Well, we really, obviously we needed to build this billion-dollar instrument to hear it because our ears couldn't possibly respond to it. It was so faint. But the instrument is picking up variations in space-time of less than a 10,000th the width of a proton over 4 kilometers. So this is an incredibly difficult and sensitive machine, which is why a lot of people thought it just wouldn't succeed.
How big is the LIGO machine?
So it's one instrument, each instrument is L-shaped, and the arms of the L are 4 kilometers long, and there are mirrors suspended at the apex and the ends, only there. It's vacuum in between. And a laser shines down the vacuum of this 4 kilometer long tube, hits a mirror at the other side and comes back, and all it does is keep track of where the mirror is. And as the mirror bobs on the wave, as the wave passes, just like something bobbing in the ocean, that motion's recorded. So it's a lot like a body of a guitar, trying to move with the wave and record it for you. In an electric guitar, it's done electromagnetically. And nobody says a guitar string doesn't actually make a sound. You're perfectly happy with the idea that you plug it into an amplifier and it makes a sound. Yeah. LIGO literally is basically plugged into an amplifier like that. And again, you can listen to it in the control room.
Einstein thought that black holes were a mathematical oddity.
Yeah, he did.
But obviously,
which is
modern.
Sensible.
It is. I was going to say, how could Einstein be so dumb?
I know, he's that dummy.
Obviously, modern astrophysics has proven that they are actual things. But why did he make that call, and how was he proven wrong?
Well, so the mathematical result was based on the artificial circumstance of pretending all the mass of a star was concentrated, let's say a star, at one point. And there was no explanation for how you were going to do that. How are you going to take the sun, for instance, and crush it down to a point? How could you possibly do that? I mean, I would have a very hard time crushing this chair. It's going to resist any attempt at crushing it. And people wondered, well, is the gravitational force strong enough to get a sun to collapse under its own weight eventually? And it doesn't, because the sun's hot and it puffs out. But eventually, people realized after a lot of work that when it runs out of nuclear fuel in its interior, a star that's heavy enough, and the sun is not, a star that's massive enough will collapse and will succumb under its own weight, and there will be no forces which can resist collapse. And that's actually surprising. You would think eventually the pressures of matter crushed against matter would just resist compression. But we know now from nuclear physics that it actually cannot resist the compression if the object's heavy enough. And so it will collapse down to a point. Now, you said a black hole's a thing, but the weird part is that the black hole really is nothing. There's really nothing there. So after the star collapses, it creates such a strong gravitational force around it that not even light can escape. That creates this shadow, the event horizon, and then the star just keeps falling. And so if you were to cross that shadow, there's nothing there. So the material of the sun...
There's not even the force of...
There's gravity, but it's empty space-time. There's no stuff there.
Once a black hole is created or born, is there always... Is that force happening forever? That suckage? Yep. That's my non-scientific term.
It's always... It's that the curves in space-time are left behind almost like an archaeological remnant. And they remain there. Space-time remains this strongly curved space even after the matter goes. So where it goes, we don't know. Maybe it's still at the center, we don't really know, and that's really a fascinating area of research. But at the shadow, the event horizon, there's nothing there.
And so if you, no matter how many millions, billions, whatever years ago, the black hole was born, you could never safely cross the event horizon.
No,
You're gone.
There's no undoing it. Yeah, the event horizon is one way; it doesn't undo.
Do you think that they've kind of, with our sort of, speaking for myself, our lay knowledge of black holes, that they've become part of our kind of poetic consciousness?
Sure. I mean, this is also relevant to your question. Why should we care if black holes collide? I mean, we care. We do because we're curious animals. That's what we are as animals. We theorize about the world all the time. We've always had some cosmology story, even if it wasn't rooted in science. You know, now we just have one that's rooted in science. The universe was born. There was a beginning. It was 14 billion years ago, and it's inhabited by these amazing creatures like black holes and you know, us, and maybe other life forms. And it's really hard to turn away and think, oh, it's much more interesting to watch reality TV. I mean, I think the much more relevant question is why we're interested in the other things, right, that have distracted us, I think, from maybe bigger picture stuff.
Jana, thank you for blowing my mind. Really, thank you for
now I'll
coming
do your
by.
makeup.
Oh, perfect. That's all we have time for. Whatever we can't fit into this half hour, we'll share on our Science Goes to the Movies Facebook page. And if you want to watch past episodes, check us out at www.cuny.tv under the Science tab.